Towards a post-quantum cryptography in blockchain, the paper emphasizes the need for implementing post-quantum cryptography to attain quantum resistance in blockchains. It highlights the potential threat quantum computers pose to most cryptocurrencies, necessitating a new cryptographic approach. The author, Tatsuru Kikuchi, presents this work as a response to the evolving landscape of cryptography and blockchain technology. This paper serves as an introductory review on theoretical cryptography and quantum information theory, laying the groundwork for further exploration into post-quantum cryptography in blockchain applications. It is essential reading for researchers and stakeholders interested in the future of secure blockchain technologies in the era of quantum computing. The emergence of quantum computers poses a significant threat to traditional cryptographic systems, particularly in the context of blockchain technology and cryptocurrencies. This necessitates the development of post-quantum cryptography, also known as quantum-resistant cryptography, to ensure the security of digital transactions. One approach to achieving this is through quantum key distribution, QKD, which leverages the principles of quantum information theory to establish secure encryption keys. Unlike traditional public key cryptography, which relies on the computational difficulty of elliptic curve cryptography over finite fields, QKD's security is rooted in the fundamental principles of quantum mechanics. The key feature of QKD is its ability to detect any attempt to measure or eavesdrop on the encrypted data, which would disturb the quantum state and cause it to collapse from a superposition of states to a single state that differs from the original. This property makes QKD an attractive solution for secure communication. Cryptography is the foundation of secure communication, enabling the exchange of transactions between two parties in the presence of adversaries. A deep understanding of cryptographic algorithms is crucial for developing robust post-quantum cryptography solutions. In this context, QKD offers a promising approach to securing digital transactions against potential quantum attacks. The encryption scheme is formally defined by a tuple E equals gen ens dec with a finite size message space M. The key generation algorithm, gen, outputs a key k chosen according to some distribution, resulting in a key space k. The encryption algorithm, ens, takes a key k and a message M, outputting a ciphertext C. The decryption algorithm, dec, takes a key k and a ciphertext C, outputting the original plaintext M. A perfect secure encryption scheme has the property that for all messages M0 and M1, and any ciphertext C, the probability of encryption is the same for both messages. This leads to the theorem stating that for a perfect secure encryption scheme, the key space size must be greater than or equal to the message space size. The one-time pad is a specific encryption scheme with the property that for a given positive integer L, the encryption scheme E equals gen, ens, dec, satisfies a particular condition. This condition ensures that the encryption scheme maintains perfect security, making it an important example in cryptography research. The one-time pad is a secure encryption scheme that has been studied extensively in cryptography. It is defined as an encryption scheme, gen, ens, dec, with a finite size message space M, where keys, messages, and ciphertexts are bit strings of the same length. The key generation algorithm chooses a key from the set k equals 0, 1, L according to the uniform distribution. The encryption algorithm outputs the ciphertext C equals k circled plus M for a given key k and message M. The decryption algorithm outputs the message M equals k circled plus C for a given key k and ciphertext C. The one-time pad is considered a perfect secure encryption scheme, as per Theorem 2.2. This means that it provides the highest level of security, making it impossible for an adversary to gain any information about the encrypted message without the key. Shannon's theorem, also known as Theorem 2.3, asserts that an encryption scheme with a finite size message space M is perfect secure if and only if two specific properties hold. These properties are that every key k element of k is chosen with equal probability, and for every m element of M and c element of C, there exists a unique key k element of k such that ens, k, m, equals c. In addition to perfect security, the text introduces the concept of an attack game, specifically Game 1, which is related to semantic security. In this game, an adversary A is presented with two experiments, where they compute two messages M0, M1 element of M of the same length and send them to the challenger. The challenger then computes a key K element of K, encrypts one of the messages, MB, using the encryption algorithm, and sends the resulting ciphertext C to the adversary. This game is used to test the security of encryption schemes against various types of attacks. The security aspects of encryption schemes are discussed, focusing on semantic security, message recovery security, and their relationship. Semantic security is defined as the difference in probabilities of an adversary outputting one in two different experiments. A cipher is considered semantic secure if this advantage is negligible for all efficient adversaries. Message recovery security involves an adversary trying to recover the original message from the encrypted ciphertext. The message recovery advantage is the difference between the probability of winning the game and the probability of randomly guessing the correct message. A cipher is secure against message recovery if this advantage is negligible. Theorem 2.4 states that if a cipher is semantic secure, it is also secure against message recovery, implying semantic security is a stronger security notion. The concept of parity prediction security is introduced through Attack Game 3, where an adversary tries to predict the parity of a given message. This sets the stage for further discussions on this topic in subsequent sections. In cryptography, a cipher E equals gen, ENS, DEC, is defined over K, M, C, and consists of key generation, encryption, and decryption algorithms. The security of such ciphers against parity prediction is crucial, where an adversary attempts to predict the parity of a message M element of M using an encrypted version C element of C. The adversary's success is measured by their message recovery advantage, parity-adva, A, E, defined as the probability of correctly predicting the parity minus 1/2. According to Theorem 2.5, if a cipher E is semantically secure, it is also secure against parity prediction. This implies that for any efficient adversary A, the value parity-adva, A, E, is negligible, indicating a low probability of successfully predicting the parity. Negligible functions are those that approach zero as the input increases, satisfying the condition that for all positive constants C and large enough inputs n, the function's absolute value is less than 1 over n raised to the power of C. Corollary 2.1 provides an alternative characterization of negligible functions, stating that a function f is negligible if and only if the limit of f, n, divided by n raised to the power of c approaches 0 as n goes to infinity. Additionally, superpoly and polybounded functions are introduced. A superpoly function is one where its reciprocal is negligible, while a polybounded function has an absolute value bounded by a polynomial in the input. Efficient algorithms, which take a security parameter lambda and other parameters encoded as a bit string, are critical in cryptographic protocols, emphasizing the importance of computational efficiency. The authors introduce several key concepts in computational cryptography, starting with efficient probabilistic algorithms. These algorithms have a running time bounded by a polynomial function and are probabilistic, meaning their outputs vary due to randomness. They also discuss system parameterization, which involves generating a system parameter given a security parameter. This parameter is crucial for setting up cryptographic protocols and ensuring their security. The authors further define families of spaces with system parameterization, requiring efficient recognizability, sampleability, and a length function. Finally, they discuss computational ciphers, which consist of encryption and decryption algorithms using a secret key, ensuring that encrypted messages can only be decrypted with the correct key. The authors introduce a framework for cryptographic primitives, consisting of three families of spaces, K, M, and C. These spaces possess desirable properties, including efficient recognizability, efficient sampleability, and efficient length functions. Specifically, K is efficiently sampleable, and M has an efficient length function. The authors defined two algorithms, ENS and DEC, which operate on these spaces. ENS is an efficient probabilistic algorithm that takes inputs lambda, k, and m, where lambda is a natural number. Lambda is an element of the support of p, lambda, k is an element of k lambda, and m is an element of m lambda. ENS outputs an element of C lambda, lambda. DEC, on the other hand, is an efficient deterministic algorithm that takes inputs lambda, lambda, k, and c, where lambda is a natural number. Lambda is an element of the support of P. Lambda, k is an element of k lambda, lambda, and c is an element of c lambda, lambda. DEC outputs an element of m lambda, lambda or a special symbol indicating rejection. The authors further establish a fundamental property of the encryption and decryption schemes, namely that for all lambda, lambda, k, m, and c satisfying certain conditions, m equals DEC, lambda, lambda, k, c. This property ensures the correctness of the encryption and decryption processes. The authors also discuss the concept of a stream cipher, specifically a modified one-time pad scheme with a shorter encryption key length. In this scheme, the encryption key is given by an LBIT string, where L is less than L, the length of the plaintext and ciphertext spaces. The encryption and decryption functions are defined as ENS, S, M, equals G's circled plus M and DEC, S, C, equals G's circled plus C, respectively, where G is a function that maps the LBIT string S to an LBIT string. The concept of stream ciphers is based on symmetric encryption, where plaintext digits are combined with a pseudorandom cipher digit stream. The security of this cipher relies on the properties of the pseudorandom generator, PRG, used to generate the cipher digit stream. According to Shannon's theorem, a stream cipher by itself cannot achieve perfect security, but if the PRG satisfies certain security properties, it can be semantically secure. A PRG takes a seed input and produces a pseudorandom output, consisting of two families of spaces with system parametrization P. S equals S lambda, 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 lambda and R equals R lambda, 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 lambda. The algorithm G is an efficient deterministic algorithm that outputs an element R element of R lambda, lambda when given inputs lambda, lambda, and S, where lambda element of N, lambda element of sup, P, lambda, and S element of S lambda, lambda. The attack game for a PRG involves an adversary trying to distinguish between the output of the PRG and a truly random string. The adversary's advantage is measured as the difference in probabilities of the adversary outputting a bit 1 for a given bit B element of 0, 1, highlighting the importance of the PRG's security properties in maintaining the security of the stream cipher. In the realm of cryptography, pseudorandom number generators, or PRGs, play a crucial role in ensuring the security of encryption algorithms. A secure PRG is defined as one where the advantage of an efficient adversary, denoted by PR-GADVA, A, G, is negligible. This concept is fundamental to the construction of stream ciphers, which utilize PRG algorithms to generate a sequence of random bits. In a stream cipher, the encryption scheme involves XO-ring the plaintext with the PRG-generated sequence, while the decryption scheme involves XO-ring the ciphertext with the same sequence. In contrast, block ciphers operate on fixed-length blocks of plaintext, employing deterministic algorithms to produce corresponding ciphertext blocks. The Advanced Encryption Standard, or AES, is a prominent example of a block cipher, highlighting the importance of judicious key selection and random permutations in ensuring the security of these algorithms. The distinction between PRG security and stream ciphers is critical, as it directly impacts the confidentiality and integrity of encrypted data. By understanding the technical intricacies of these concepts, including the definition of a secure PRG and the construction of stream ciphers, researchers and practitioners can develop more robust and secure encryption protocols. The authors explore the security aspects of block ciphers, focusing on unpredictability. They introduce a new attack game, Attack Game 5, to assess a block cipher's security against an adversary. In this game, the adversary is presented with either a block cipher or a random permutation and must distinguish between them. The adversary's advantage, denoted as BCAD-V, A, E, is the probability difference between the events where the adversary outputs a bit 1 for each scenario. A secure block cipher, E, is defined as one where for all efficient adversaries A, the value BCAD-V, A, E, is negligible. This means no efficient adversary can significantly distinguish between the block cipher and a random permutation, ensuring unpredictability. The authors also discuss the prediction game, where an adversary tries to predict the output of the block cipher for a new input after observing previous outputs. If a block cipher is secure, every efficient adversary will win this prediction game with negligible probability. The unpredictability of a block cipher is crucial for its security against key recovery attacks. If a cipher is unpredictable, an efficient adversary will win the key recovery game with negligible probability. The concept of key recovery games involves an adversary outputting a candidate key, winning if the candidate matches the actual key. The key space size is vital, as a non-super poly key space allows an adversary to win by random guessing. Exhaustive search attacks, where the adversary makes a few queries to increase the probability of finding the correct key, are also discussed. The page concludes by defining an ECB cipher and its variants, emphasizing the importance of the block size in the encryption process. In the context of cryptography, a block cipher is defined as a symmetric key cipher that operates on fixed block sizes, typically encrypting plaintext blocks into ciphertext blocks of equal length. The security of these ciphers relies on the complexity of the encryption and decryption functions, which are often based on substitution permutation networks or Feistel ciphers. The construction of an LWISE electronic codebook, ECB, cipher, derived from a block cipher E, is discussed. This ECB cipher, denoted as E, is defined over a message space restricted to sequences of at most L distinct data blocks. The theorem states that if the original block cipher E is secure, then the derived ECB cipher E is semantically secure. In practice, block ciphers are constructed using the iterated block cipher scheme. This involves choosing a simple block cipher, known as the round cipher, and a pseudorandom number generator, PRG. The PRGG is used to generate a sequence of pseudorandom keys from a single key K, which are then applied iteratively to encrypt or decrypt the message. The key expansion function generates an n sequence of pseudorandom keys, K1, Kn, from K, as shown in equation 17. The iteration process for encryption involves applying the encryption function with each generated key, starting with the first key K1 and ending with the last key Kn, as depicted in equation 18. For decryption, the process is reversed, applying the decryption function with the round keys in reverse order, as shown in equation 19. This highlights the importance of block ciphers in cryptography and their construction through the iterated block cipher scheme, emphasizing the significance of the ECB cipher and its relationship with the original block cipher's security. The data encryption standard, DE, is a well-known algorithm in round ciphers, with its strengthened version, triple DES, 3DES, consisting of 3 rounds and having a key length of 168 bits. Although approved by NIST until 2030, it was surpassed by the Advanced Encryption Standard, AES, in 2002, which features a more secure 128-bit key space and 10 rounds. A hash function H is a deterministic algorithm that takes a key K and a message M as inputs, producing a digest T equals H, K, M. The hash function is defined over the space, K, M, T, where T is the digest space. A collision occurs when two messages M1 and M2 form the same digest under the same key K, i.e., H, K, M1, equals H, K, M2. Since the size of T is smaller than M, collisions are common. However, for cryptographic purposes, it is essential to have a collisionless property, where an adversary cannot find a collision without any information on the keys. The weak collisionless property is sufficient in practice, where the adversary must find a collision without any information on the keys. In cryptography, a game between an adversary A and a hash function H is defined, where A wins if two messages collide under H. The adversary's advantage, UH A, H, is the probability of winning this game. A hash function H is considered an O-bounded universal hash function, or UF, if UH A, H, is less than or equal to O for all adversaries A, meaning that the probability of two distinct messages colliding under H is bounded by O. If O is negligible, then H is a statistical UHF. If UH fadiv, A, H, is negligible for all efficient adversaries A, then H is a computational UHF. A trapdoor function scheme is also defined as a tuple of efficient algorithms E equals, gen, ens, dec, along with two families of spaces with system parameterization P. M equals, M lambda, 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 lambda and C equals, C lambda, 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 where lambda element of N and lambda element of sub P, lambda. The scheme must have the property that M is efficiently recognizable and sampleable. This concept is crucial in public key encryption, where the goal is to ensure secure communication by using a pair of keys, a public key for encryption and a private key for decryption. The concept of a trapdoor function scheme is a cryptographic primitive that enables efficient encryption and decryption of messages. It consists of three algorithms: key generation, gen, encryption, ens, and decryption, dec. The key generation algorithm outputs a pair of keys, pk, sk, given an input lambda element of n and lambda element of sub p, lambda. The encryption algorithm takes inputs lambda element of n, lambda element of sub p, lambda, pk, and m element of m lambda, lambda, and outputs an element of c lambda, lambda. The decryption algorithm takes inputs lambda element of n, lambda element of sub p, lambda, sk, and c element of c lambda, lambda, and outputs an element of m lambda, lambda. The RSA scheme is a famous example of a trapdoor function scheme. The RSA trapdoor permutation scheme E equals, gen, ens, dec, is parametrized by fixed values of L greater than 2 and E greater than 2. The key generation algorithm RSA gen outputs a pair of integers, n, d, equals RSA gen, L, E, where n equals pq with p, q being distinct primes, and d equals E1, mod, p1, q1. The decryption process is defined as CD for a given secret key SK and C in Zn. A public key encryption scheme, denoted by E, consists of three components: gen, ens, and dec. Gen generates a public key and a secret key, ens encrypts a message using the public key, and dec decrypts the ciphertext using the secret key. The RSA trapdoor permutation scheme is defined, involving an adversary's attempt to break the encryption. The RSA assumption holds if the adversary's advantage in breaking the encryption is negligible. The quotient group, Z, NZ, times, specifically for the case where n is a prime or a power of 2, is a key focus of this discussion. For a prime p, the order of the quotient group is determined by Euler's Totient function, which equals p1. The group becomes cyclic if and only if n equals 1, 2, 4, a prime p, or 2 times a prime p raised to a power greater than 0. The cyclic group Cn is defined as Z, Nz, times equals C phi, n, where phi, n, represents Euler's Totient function. This concept is crucial for understanding the properties of cyclic groups, where each element can be expressed as a power of a generator G. Additionally, the Diffie-Hellman key exchange protocol relies on the difficulty of computing G-ab, given G-alpha and G-beta, where alpha and beta are integers and G is a generator of the cyclic group. This computational difficulty is a fundamental assumption in cryptographic systems. The attack game, introduced in definition 2.32, involves a cyclic group CP1 with prime order P, generated by an element G. An adversary A is given a pair of outputs, U, V, where U equals G alpha and V equals G beta for randomly chosen alpha, beta in ZQ. The goal is to compute a value W in CP1. The event WB is defined as the adversary outputting a bit 1 for a given bit B in 0, 1, and the event W1 occurs when the adversary wins the game, meaning W equals W. The advantage of the adversary A in solving the decisional Diffie-Hellman problem with CP1 is quantified as dd had V, A. CP1 equals P, W0, P, W1, where P, W0, and P, W1 are the probabilities of the events W0 and W1, respectively. The decisional Diffie-Hellman (DDH) assumption introduced in definition 2.33, holds for CP1 if the value of dd had v, a. CP1 is negligible for all efficient adversaries A. This assumption is crucial in cryptographic constructions, providing a foundation for secure key exchange and encryption schemes. In quantum cryptography, fundamental concepts include qubits, entanglement, and quantum gates. A qubit is a superposition of 0 and 1, represented in the Hilbert space H equals C2. A single qubit state can be written as a state in the Hilbert space, with the basis Bz equals 0 close angle bracket, 1 close angle bracket, and this basis can be changed to another one using a unitary transformation. To construct an n-qubit system, single qubit systems are combined by taking n-tensor products of the Hilbert spaces. For example, a 2-qubit state is spanned by 4 basis states, taking into account orthogonal conditions. This 2-qubit state can be expressed by taking the tensor product of 2 Hilbert spaces, H1 circled times H2 equals C2 circled times C2, as described by the equation. Entanglement, a crucial concept in quantum information theory, refers to the quantum correlation between different qubits. The density operator ρ associated with a given qubit is defined as ρ equals psi open angle bracket psi, playing a key role in quantum cryptography. In quantum computing, a qubit is considered a pure state when its density operator satisfies the condition of being equal to its square, as expressed in equation 34. This implies that a qubit state in the Hilbert space H1 circled times H2 is a pure state when it can be expressed in the separable form of psi1 circled times psi2. Conversely, a qubit state that cannot be written in this separable way is referred to as an entangled state. The standard basis for 2 qubits consists of 4 orthonormal states known as the Bell states, which are maximally entangled. These states can be expressed as psi plus or minus 1 equals 0 plus or minus 10, square root 2 and psi plus or minus 2 equals 0 plus or minus 11, square root 2. A unitary operator that acts on a small number of qubits is called a quantum gate, the quantum equivalent of classical gates such as AND, OR, and NOT. These gates are defined by the outer products of basis states in the Hilbert space H. For instance, the Pauli matrices are examples of 1-qubit gates, with the identity gate I, Pauli X gate X, Pauli Y gate Y, and Pauli Z gate Z being defined as specific combinations of basis states. Notably, the Pauli matrices are fundamental components in quantum computing, playing a crucial role in the implementation of various quantum algorithms and quantum error correction codes. By leveraging these gates, researchers can manipulate and control qubit states, enabling the execution of complex quantum operations. Quantum gates are fundamental components in quantum computing, enabling the manipulation and control of qubits. The bit flip gate X and phase flip gate Z are 2 basic quantum gates that play a crucial role in quantum computation. The bit flip gate flips the state of a qubit, while the phase flip gate changes the phase of a qubit by pi radians. The phase shift gate R-phi is another important quantum gate, which shifts the phase of a qubit by an arbitrary angle phi. This gate is particularly useful in creating superpositions and entanglements, essential for quantum algorithms. The Hadamard gate H is a key gate in quantum computing, as it transforms a qubit into a superposition state. When applied to a qubit in the state 0, the Hadamard gate creates an equal superposition of 0 and 1. This property makes it a fundamental gate for initializing qubits in quantum algorithms. The controlled NOT gate CNOT is a 2-qubit gate that performs a conditional flip operation. It flips the state of the target qubit if and only if the control qubit is in the state 1. The CNOT gate is essential for creating entangled states and performing quantum teleportation. In summary, these quantum gates form the building blocks of quantum computing, enabling the creation of complex quantum algorithms. Their precise manipulation and control are critical for harnessing the power of quantum computing. The CNOT gate, a fundamental quantum gate, is introduced in matrix form as expressed in equation 37. This gate plays a crucial role in quantum teleportation, where Alice possesses a qubit psi, expressed as a superposition of basis states 0 and 1, as shown in equation 38. She shares an entangled pair of qubits with Bob, one of which is in the Bell state psi plus 2, given by equation 39. The total state of the system is represented as the tensor product of psi and psi plus 2, resulting in a four-term expression. Upon performing a Bell measurement on the entangled pair and the target qubit psi, Alice obtains one of four possible Bell states, which can be encoded by two classical bits, as indicated in equation 40. Depending on the measurement outcome, Bob performs one of four actions on his qubit to recover the original state psi, resulting in the qubit phi. This process highlights the importance of entangled states and Bell measurements in facilitating the transfer of quantum information between Alice and Bob. The CNOT gate, a key component in this process, enables the manipulation of qubits and the creation of entangled states, essential for quantum teleportation. The protocol relies on the shared entangled pair, allowing Alice to transfer the quantum state psi to Bob without physically moving the qubit. This foundation in quantum teleportation has significant implications for quantum communication and information processing. In quantum transportation, Bob receives the correct qubit from Alice following a Bell measurement. This process relies on the concept of von Neumann entropy, which quantifies the uncertainty of a quantum state. Defined as S, ρ, equals Tr, ρ lane ρ, von Neumann entropy possesses key properties. It is non-negative, equal to 0 for pure states, and reaches a maximum value equal to the dimension of the Hilbert space. The relative entropy, a crucial concept in Holevo's theorem, is also introduced. This theorem outlines the conditions under which quantum information can be reliably transmitted over a quantum channel. Holevo's theorem states that the amount of classical information that can be transmitted via a quantum channel is bounded by the Holevo capacity, chi. This capacity is calculated as the maximum of the Holevo information, chi, ρ, e, over all possible encodings, e. The Holevo information, in turn, is defined as the difference between the von Neumann entropy of the quantum state and the average von Neumann entropy of the measurement outcomes. This theorem has significant implications for quantum communication, as it provides a fundamental limit on the transmission of classical information over quantum channels. In essence, Holevo's theorem establishes a connection between the quantum information transmitted and the classical information that can be decoded from it, enabling the reliable transmission of quantum information over noisy channels. The paper delves into entangled states and the total density operator ρ, emphasizing the Holevo information chi as an upper bound for information attainable through a Bell measurement. This concept is pivotal for understanding quantum information theory's limitations. It then transitions to quantum key distribution, focusing on the BB84 protocol. This protocol involves Alice's random bit and basis selection, encoding and sending a qubit to Bob, Bob's basis selection, measurement, and decoding. The goal is to securely share a secret key between Alice and Bob. In the BB84 protocol, a fundamental quantum key distribution method, Alice and Bob exchange bits through repeated iterations until a substantial amount is accumulated. Subsequently, they publicly share the basis employed for encoding and decoding, discarding bits where the basis differs. To validate the security of the protocol, they publicly compare a subset of their bits, verifying agreement. If consensus is reached, they retain the secret key, otherwise, they restart the process. However, a critical loophole exists, enabling Eve to gain information on the exchanged bits. This vulnerability is exemplified by considering different bases for Alice, Bob, and Eve. Notably, when Alice and Bob share the same basis, the probability of detecting Eve's presence after discarding bits is 1/2. This highlights the significance of addressing this loophole to ensure the protocol's security and integrity. The BB84 protocol, a quantum key distribution protocol, is applied in cryptographic algorithms for blockchain technology. The protocol involves three parties: Alice, Bob, and Eve in the quantum key distribution process. Table 1 illustrates how each party's bits, bases, and qubits are used to establish a secure key. The probability of not finding Eve by revealing one bit is calculated to be 3/4, increasing as more bits are given away. The probability not to find Eve by giving away k bits is expressed as pk equals 3/4 k, with the probability of finding Eve being 1 pk. Additionally, the page discusses cryptographic algorithms used in blockchain, categorized into three types: cryptographic hash functions, symmetric cryptographic algorithms, and asymmetric cryptographic algorithms. These algorithms are crucial for securing data and ensuring the integrity of blockchain transactions. The fundamental differences between symmetric and asymmetric cryptographic algorithms are discussed, emphasizing the significance of key distribution in these methods. The importance of standards is highlighted, citing the Federal Information Processing Standard, FIPS, and the National Institute of Standards and Technologies, NIST, Special Publication, SP, for standardization procedures. The security properties of cryptographic hash algorithms, including one-way functions, weak collision resistance, and strong collision resistance, are detailed. The overview of symmetric cryptographic algorithms, which utilize a single secret key for both encryption and decryption, underscores the importance of security, mentioning several approved methods by NIST. The protection of sensitive data is a crucial aspect of modern cryptography, with symmetric and asymmetric algorithms being the primary methods employed. Symmetric algorithms use the same key for both encryption and decryption, whereas asymmetric algorithms utilize a pair of keys, a public key and a private key. Digital signatures, a type of asymmetric algorithm, ensure identity, integrity, source, and non-repudiation. The FIPS 186 standard specifies approved algorithms, including RSA, ECDSA, and EDDSA, detailing key sizes and methods for generating key pairs. The RSA scheme, although mathematically secure, is not commonly used in cryptocurrencies due to the integer factorization problem. The ECDSA scheme is also approved and specified in FIPS 186. The digital signature schemes discussed include RSA, ECDSA, and EDDSA. RSA, known for its simplicity and security, is widely used. However, ECDSA has surpassed RSA in terms of security and key size, being adopted by major cryptocurrencies like Bitcoin, Ethereum, and Ripple. EDDSA, although less widely adopted, is deterministic and used by some cryptocurrencies such as Monero, Zcash, and Stellar. Key establishment schemes are also crucial for secure communication, with two main types: discrete log-based schemes and integer factorization schemes. The latter includes RSA, approved for key establishment, digital signature generation, and verification. Discrete log-based algorithms like Diffie-Hellman, DH, and MQV are approved for key agreement. The application of cryptographic techniques for verification of digital signatures is a crucial aspect in the context of key establishment. Specifically, it involves the use of algorithms to ensure the authenticity and integrity of digital messages. This process relies on the generation of a unique digital signature, which is then verified using the sender's public key. The research paper discusses the application of machine learning algorithms to analyze and predict the behavior of complex systems. Specifically, it focuses on the use of neural networks to model and forecast the dynamics of chaotic systems. The study highlights the potential of these algorithms in uncovering hidden patterns and making accurate predictions in such systems.